This is the video record for probability and stochastic process, homework 11, question 2. For the problem setting, it says that here, it is suggested that the following function of v, which the first is f of v is equal to e to the degree of minus absolute value of v, and the second b equation of v is f of v equal to sine square of v over v square, and the third condition, situation where c is a function f of v equal to 1, where the absolute value of v is less than or equal to alpha, and when the absolute value of v is larger than alpha, f of v is equal to 0, and we can illustrate the third equation as the following graph. And these three different functions may represent an autocorrelation function of a WSS stochastic process by setting v equal to tau, or spectral density function by setting v equal to omega, or both. So the problem asks us to argue and find each function f of v may represent either a WSS stochastic process or a density function, and we have to explain our answers. And so we try to look into different functions of each of these functions of fv. And as we know, if r of tau is an autocorrelation function of a real WSS stochastic process x of t, and we know it should be even, and the autocorrelation of tau is less than or equal to r of 0, and its Fourier transformation should be a non-negative function. And if S of omega is the power spectrum of WSS process x of t, then it should be non-negative. These are the basic rules we are trying to use or apply in decision whether these three equations functions are stochastic process or power spectrum of a density function. So for A, f of v equal to e to the degree of absolute value of v, and it may be represent an autocorrelation function because e to the degree of the absolute value of v is even, and it's also less than or equal to e to the degree of absolute value of 0, which is essentially 1, and e to the degree of absolute value of v, its Fourier transformation function is 2 alpha over alpha square plus omega square, which is non-negative. So it satisfies the conditions for r of tau to be a real WSS stochastic process. And for the second situation, it also may represent a power spectrum because e to the degree of minus absolute value of omega is larger than 0, which is non-negative. Essentially, it's proved. And for the second situation, where f of v is sine square of v over v square, the first is it may represent an autocorrelation function because sine square of v over v square is even, and sine square tau over tau square is less than or equal to the limit when tau is approaching 0. The limit if we take the limit of it, which is essentially a sine square of tau over tau square, and this limit is essentially equal to 1, and sine square of t over sine square of tau over tau square can be illustrated as this following graph, and it shows that it's non-negative on the area of definition. For the second situation, it may also represent a power spectrum. It's because the essentially sine square of omega over omega square is well, it's easy to see it's always larger than or equal to 0. For the third situation, we try to look into f of v, where when absolute value of v is less than or equal to alpha, f of v is equal to 1, and otherwise it's equal to 0. And for the first situation, it cannot represent an autocorrelation function because its Fourier transform is essentially 2 times sine alpha omega over omega, which is non-negative, and this contradicts the definition of a WSS stochastic process. The second situation, it may represent a power spectrum, is also because f of v is or f of omega is always larger than or equal to 0. This is the end of this video record.